I'm going to finish this class with a couple of, I'm not quite sure what to call them. I call them basic algebra uses, but in fact one of them is a potential application that we're going to see later, and another one is a basic property. So, well, think of them as you wish. The first one is the following. Once you know how to multiply two things, you pretty much have an idea of how to take a power of one thing, right? So remember, what does it mean to compute the square of a number? It just means you take the number and you multiply by itself, right? Same thing with cubes and so on. So now that we have a matrix product, we should be able to define and give meaning to the idea of the power of a matrix, okay? And certainly we can do that. But because of the restriction that we have on the dimensions of the matrices, we can only do this for square matrices. In order to multiply a matrix by itself, I have to make sure it has the same number of rows and columns, otherwise I cannot take the dot product of one row with one column. Okay. But once that is done, once we've restricted our attention to square matrices, then I can define a squared as a times a cubed as a times a times a, and of course the associativity property tells us it doesn't matter which order we do it. In fact, of course, in this case, the product is even commutative because, of course, if I multiply a by itself, it doesn't really matter which order I think of it, right? And then I can take these powers as high as I want. One problem with this, or one restriction with this idea of power, however, is that we have defined a product of matrices, but we will not define a division of matrix. We'll define something else that could be interpreted in some ways as dividing a matrix by another, but it's not really. Okay, so think more generally, think of the fact that no, there is no division of matrices, and we're going to see later. We're going to discuss at length later on why that is the case, that we cannot really divide even though we can multiply two matrices. And because of that, we're not going to have any negative powers of matrices to worry about, and we're not also going to take any fractional powers or any such complications. So as far as powers of matrices, we're only going to consider positive integer powers. The other thing to keep in mind about a matrix product is that a linear system can actually be written as a matrix equation, okay? Just an equation involving just a matrix. How does that work? Well, remember, a linear system looks like this. It's a bunch of equations, each of which on the left hand side has a dot product of what? Of the vector of variables that I'm calling x times one row of coefficients. And we've seen that we can actually, if we write the vector of variables as a column vector, now what we're doing is we're multiplying each of the rows of the matrix of coefficients times the column given by the variables. And then we're setting that equal to each of the constants. Okay? So written another way, I can think of that system of equation as this matrix equation. We have the matrix given by the rows of coefficients times the matrix given by the column of variables equal to the matrix given by the column of constants. Now, if you're tempted to tell me that those are not matrices, those are vectors, I remind you that every vector is a matrix, and that in this context, in fact, we are thinking on the left-hand side especially of multiplying those two as matrices. I'm going to use the row by column multiplication. Notice that when I'm multiplying this, which again is definitely a matrix, times this, which is a vector and therefore a matrix, what am I doing? Because I'm multiplying a1 times the whole of this vector through the dot product, and that's what gives me the first equation. And then I'm taking the second row, multiplying by this whole column, getting the second equation. So as you can see, that is exactly the row by column product that we have defined. So if that is the case, again, that matrix consisting of A's, I've written it as a vector of rows, but I can simply write it as a matrix. X can be written as a vector and as a matrix. The constant C can be written as a vector, therefore as a matrix. And so I can write the whole system as AX equals C. What that does, we'll see later on, it allows us not only to develop another way of solving an equation, of solving a linear system. It's actually a way that looks different but is really the same as Gauss-Jordan elimination in practice in terms of computations. But it is a different perspective on that, and it's a perspective that will open our mind to more possibilities, and in particular to the option of developing new information, new features of the system and of the matrices involved. So this matrix product is very simple. In class we're going to do many simple examples that will be easy to implement, but it opens the door to a lot more stuff that we can do with matrices and vectors.